What is a set? So the common definition we know of a set is a collection of well-defined objects. Of course, later on you understand that it may be even groups of people. It is a set. So when you bring a group of things together, you form what we call a set. So an example of something we can call a set, you can say a set of maybe, let's say, mountains in Africa. So that can be as simple as a list of the mountains you can name in Africa. Okay? So you can say that set may consist of Mount Kilimanjaro, okay, and other mountains in Africa. So I can put commas and then I can cross like that. So that actually introduces us to one way in which we can present sets. So this is called roster form. Okay. Now that we understand what a set is, what exactly is set theory? So set theory is just basically a branch of mathematics. Of course, we understand it's mathematics, but deals with sets and their properties. So look at different set properties, laws under set theory, ways in which we get to present sets. Okay, so basically gets to meet the roster form which I've already shown you, and then we'll deal with Venn diagrams and also the aspect of set builder notation. Okay, so this is going to be very interesting. Of course, we get to look at the set interval notation as well to make it more interesting, and we'll look at different types of sets that are there. We'll look at different set theory symbols that we basically get to use and what they stand for, and then look at the notations, things like the union, intersection, the complement, all that. So that's where we're going to start from. We'll continue with the notations that we basically get to work with under set theory. Okay, so when we basically use these curly brackets to represent a set in roster form. So that is a set. So when there's nothing inside there, we can call that as an empty set. Okay, it is called an empty set in such a case. So we can use that to denote an empty set. Another way of denoting an empty set is something like that. A circle and then a line across it. That's an empty set. The other thing that we'd have to familiarize ourselves is something that is very common, right? That is a union. So a union. So a union is basically where you say A union B, more like a U. Okay, that is a union of a set. So what does a union mean? So a union implies you get to combine the elements in the sets. So I'll give you an example of roster form. Let's say we have set A consisting of elements 1, 2, 3. And then you have set B consisting of elements 2, 4, 6, 8. And then they ask you to find the union. So they'll tell you to say find the A union B. So union implies you combine all the elements to form one set. So preferred we arrange them in the order, okay, of increasing. So I'll begin with the smallest one. 1. Maybe to make you understand, I can even do this. Let me put a 7 there. So from set 1 we have 1 and 2 as the smallest numbers, and then we can have 4, 6, 7, 8. So there we are. So all the elements are now together, right? So let's try to assess. So we have 1, 1, 2, 2, 7, 7. 2 is also 2, 4, 4, 6, 6, 8, 8. So there's one thing that we've learned here. We've seen that despite 2 being part of both sets, 2 is part of both sets, but we've only written it once. So that's the way you basically get to deal with that. Don't write it twice. Okay? So that denotes an intersection of a set. So that's why when you look at the aspect of dealing with numbers, there is this rule. The number of elements in A plus the number of elements in B should be equal to the number of elements in the union set, and then we can say plus the number of elements in the intersection set. So this can go the other side so that it becomes minus, where you would say the number of elements in A plus the number of elements in B minus the number of the intersection elements should be equal to the number of elements in the union of what? Of a set, which is basically true. If you look at this case, how many elements are in A? We have 3. How many elements are in B? We have 4. How many are common elements? 1. In the union, we had how many elements? We had 1, 2, 3, 4, 5, 6. 3 plus 4 is 7 minus 1, 6. So that's where it comes from, that basic idea. So continuing with other notations that we have under set theory, we have also what we call intersection. A intersection B. What is an intersection of a set? Intersection of a set, as we've already seen, deals with common elements between or among the sets under discussion. Okay. So if you have set A and set B, and then you've been given the elements, if they ask you to find the intersection, you're looking at the common elements. Okay, as we saw from the previous example, 2 or Z, a common element. So that would make up the intersection of a set. Okay, so there's also an aspect of a subset. So there's a symbol for a subset. So when I say A like that, it implies that A is a subset of B. A is a subset of B. That's what it means. So what is a subset? So a subset is a set that is part of another set. So an example is if B is having 1, 2, 3, 4 as its elements. So by the way, I didn't mention that. So a set consists of what we call elements or members. And then let's say set A is now made up of 2, 3. So if you observe, you understand that 2 and 3 are part of set B, right? So that makes A to be a subset of what? Of B. That's what it means. A is part of B. That's what it means to be a subset. If something is not a subset, let's say we have set C, which is made up of 2, 7, 8. So of course we do agree 2 is part of B, but 7 and 8 are not part of set B. So in this case we can say that set C is not a subset of B. So this is a symbol for not being a subset. It's kind of like you write something like this as a C, and then you a line across it. So not a subset. That's a symbol for not being a subset. So, what other thing can we talk about? The other symbol we can talk about is proper subset. So it's an aspect of a proper subset. So without a line on the bottom, it's a proper subset. Okay. What's a proper subset? What's a proper subset? So this is a proper. So a proper subset is a subset that is as all its elements part of a set. So like in the previous example I gave you, if you have set A to have 1, 2, 3, 4, and then set B as 1, 2, 3, 4, 5. So in this case, we can say that set A is a proper subset of what? Of B, because all its elements are part of B. But in a case where we have, let's say I remove 5 from this other set, A is still a proper subset of B, but B has the same elements as A. In this case where the sets are equal, we can just say A is a subset of B, but it's not a proper subset. Of course, we'll understand later on when I'll explain the difference between a proper subset and just a subset. So of course, a proper subset is a subset, but not all subsets are proper subsets. That's a simple notation we can understand there. Okay, there's an aspect of a superset. So as we've seen, the opposite of a subset is now gives us a subset. So if you say A, and then you turn this symbol, this other side, it tells you A is a superset, proper superset. Okay? Proper superset. So if you basically get then the other symbol for just a subset, it just becomes now superset. So a superset is a set that is made up of another set. If another set is part of a set, that is called a superset. So if you again begin cutting out lines, it would imply you're refusing it is not a superset. Okay. So I did talk about other symbols like this, which is an empty set. And then another symbol we can talk about is now a power set. So understand, I'll explain what a power set is. That's a symbol for a power set. Equality, if A and B are equal, that is an equal set. Use that symbol for equality. Then we have this aspect of a complement, which we can also write as that. A complement of a set implies elements outside that given set. And then if you're saying A is a member of a certain set, you use this symbol. That symbol denotes member. Okay. If it is not a member, you can draw a line across it. It is not a member of a given set. Okay. So that is a common notations we're going to come across under our study of set theory. Okay. So I'm going to give you some of the formulas that are going to be very helpful. But before that, let me try to explain now some of the things that I said I'll explain in the next video. So now continue and look at the subsets more in details. So consider a case where you have set A consisting of even numbers less than 10. So what is a subset? So a subset would be a set which is going to have its elements being part of another set. Let's say that set is A, as we've said, and then consider having another set, let's say set B, which is having elements 2 and 4. So if you look at set B, all the elements that are in set B are part of A. So we can clearly see that B is a subset of A. So now look at the symbol I'm using. So this symbol denotes a proper subset. So a set is said to be a proper subset of another set if its superset has at least a single element which is not within set B. So in this case we have 6 and 8, which is outside, which is not part of B. So B is a proper subset. Okay. Now consider a case where we have another set C, which now will have all the elements that are in A. So in this case we can see that the number of elements are the same between A and C. So even in such a case we can clearly consider a case of a subset. So you can say that C is still a subset. Now I'm putting a dash there. So whenever you see that symbol, the easiest way of remembering is, for me, I think of it to be equal. So we can clearly see that C is an improper subset of A because all its elements are part of A and there's no other element which is outside C. So that's what we need to understand. So I think that is now a difference between a proper subset and an improper subset. C is an improper subset. B is a proper subset of A. So the other way you can think of an improper subset is by looking at the number of elements being equal or the same. That's what we're calling now an improper subset of another set. Okay, so how do you basically get to find the number of subsets of a given set? So I'll use a very simple example. I'll use the number of elements. Let's say we had 1, 2, and 3 as the elements of this set. So what are the possible subsets of that set? So an empty set is a subset. A set only containing 1 is a possible subset. A set only containing 2 is a possible subset. A set only containing 3 is a subset. Which other sets can you think of? So we can have a combination of 1 and 2 as a set. We can have a combination of 1 and 3 as a set. We can have a combination of 2 and 3 as a set. Is there any other possible combination we can have? We can also have the set itself as it is, as a subset. Remember we talked about a set being a subset of itself, which we called an improper subset. So how many of these are if we come up with? So there's 1, 2, 3, 4, 5, 6, 7, 8. So set A has got 8 subsets. So 8 is our answer. So the formula for finding the number of subsets is 2 to the power n, where n denotes the number of elements. In this case, the number of elements were 3. So 2 to the power 3 implies 2 times 2 by itself 3 times. 2 times 2 is a 4 times 2 gives us 8, which is true. Now, in terms of finding a number of possible proper subsets, 1, 2, and 3, which is an improper subset, is supposed to be removed. So that tells us that the formula for finding the number of proper subset is 2 to the power n minus the improper subset, which will always be 1. So that is the formula for finding the number of proper subsets. Okay, proper subsets, very important to understand. That formula is going to be very useful as we basically get to look at the proper subsets. Okay, now what if you look at an empty set? So if you have an empty set, let's say A is an empty set, it does have also a subset. So each subset is an empty set itself. So an empty set is an improper subset of itself because it matches up with its original set. So that is a basic introduction to subsets. I believe you understand the notation of proper and improper subsets and what a subset is and how we have to find how many there are for a given set. We'll now look at what we're calling a power set. So what exactly is a power set? So a power set is a set that is made up of all the subsets of a given set. A as a set with the common elements we are using 1, 2, 3. Okay. So we did indicate from the previous video under subsets, but set A had the 8 subsets. So a power of this set, which is what we're calling a power set, denoted with a capital letter P. Okay, that symbol is for a power set. So how do you basically show the power set? So it's going to be a capital letter P, and then in the brackets you put the set itself. So you use the curly brackets as we have to open. So we said the first subset is going to be an empty set itself, and then of course we can also have the improper subset, which is having the exact number of elements from the set itself. So by the way, the order doesn't matter. Okay, so you'll be putting commas to separate these subsets. So the other subset you can think of, we said 1 is a subset, we said 2, we said 3. So I'm now writing so fast. We said 4. There's no 4. So now we'll begin combinations 1, 2, 1, 3, 2, 3. Are they already 8? Remember we said the number of subsets of any set is to the power, so in this case it's supposed to be 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the set is full. We can now close. Don't forget about the commas. Okay, so this is a power set, a set that is made up of all the subsets of that given set or the set under discussion. We'll begin looking at a complement set. So what is a complement set? A complement set, denoted as usually denoted as A with a dash. In some other box they use a C. So what is a complement of a set? But what exactly does it mean? So this requires us to understand what a universal set is. A universal set is a set that indicates all the elements under discussion. Okay? So if it may be, for example, all the natural numbers from 1 up to 10. Okay? We'll take that as our universal set in this case, all the way up to 10. So now let's say we have set A, which is having elements, the even numbers. Okay? So if you're asked to find, say, find the complement of a set A, which is like that, or AC, how would you find that? So a complement basically means the elements outside a given set, but within the universal set. In other terms, you can think of a complement of a set as the set itself, remove, or it's not like that. It's actually the universal set that you have, remove the elements in that set. So a complement of a set involves the elements outside the given set, but within the universal set. So it's more like what elements are outside A, but are still within the universal set. So look at the numbers like 1, 3, 5, 7, 9. So that is basically what the A complement is going to consist of. Elements outside the given set, but within the universal set. So it would be wrong for me to get a number like 11 just because it is not in A. So it only qualifies if it is a member of the universal set. That's what a complement means. So you can now feel free to practice using the very universal set that we had from 1 to 10. Now consider set P, which is made up of 1, 2, 5, 6, 9. Find its complement. Okay? We can start from there. And in addition to that, we can also find the intersection between A complement and B complement. The difference of sets A minus B. What does it mean when you see A minus B? Okay, so A minus B, under set theory, it means A without B. As simple as that sounds. A minus B means A without B. It's very, very simple and straightforward. So how would you present that? So A without B, in this case, means that remove all the elements that are within B from A. Remove them from A. So in other terms, if we look at that, the way I like approaching this is I'll look at my set A. So if you look at set A, we've got 2, 4, 5, 7, and 9 as the elements. So we'll remove all the elements that are in B because we are saying A should be without B. A minus B, A without B. So we can see that 2 is part of B. We can also see that 5 is also part of B. So 2 and 5 are the common elements. So 2 and 5 are supposed to be removed from A. So what remain in A will remain with 4, 7, and 9. That's what it means. And what doesn't it mean? What it doesn't mean is some of the students, what they do is they will remove 2 and 5 and then they'll add the 1, the 8, and the 10. That is wrong. Wrong. Only indicate the elements within A and exclude the ones that are from B. Don't add the ones in B to A. That's wrong. Okay, so try out this one. Pause the video and try out this one. B minus A. So B minus A means B without A. Okay, so I'll introduce you another way of in which I approach this question. So B, I know is consisting of 1, 2, 5, 8, and 10. So we are saying minus set A, which is having 2, 4, 5, 7, and 9. We need to make sure that all the elements of A are removed from B. So which are these? 2 and 5. What remains? We have 1, 8, and 10. So B minus A means B without A, or remove the elements of A from B. That's the difference of sets. So a few things that you can take note of, maybe even without raising that, a few things that we can take note of using B minus A. Let's try to find the intersection of A and B. We understand that the intersection of A and B, we are looking at the common elements. So the common elements were 2 and 5, right? 2 and 5 are the common elements. So you will begin now to notice essentially that if you are taught to find A minus B, it is the same as set A, and then you remove what? Minus the intersection. So all we were doing was we were just removing the intersection. Even if you look at B minus A, all we did is we removed the intersection from what? Set B. So 2 and 5 was the intersection between the two sets. So we got 1, 8, and 10 as our solution. And then the other thing that you'd have to note as well, if you say A minus B, this is the same as A intersection B complement. That's what it means. But again, you're not that's what it means. It's true. It's an identity. Okay, so others will tell you to say this minus becomes intersection, had the complement on B. Yes, it is true. But thinking of it as A without B is simpler and faster. But for the sake of simplifying sets later on, A minus B means A intersection B complement. So you know how to find the complement of B, and then you know how to find the intersection of sets. So you can essentially get to prove the solutions. Take your inverse set to have been 0, let me say 1 all the way up to 10. And then try to prove that A minus B is equal to A intersection B complement. Okay, that's where we start from. Continue from there to progress and look at now the laws under set theory. De Morgan's laws. So this is where we're going to begin looking at the laws under set theory. Okay, so we've already seen how we basically get to work with roster form. We understand the notations of intersection and union. So we first De Morgan's law, as we can see. Consider a case where you have A intersection B in brackets and then you have a complement outside. So what will basically happen is we expect the notation in between to change from intersection to union. And then we expect that set A becomes complement and B complement as well. So you might guess what the other De Morgan's law tells us. So if you look at the De Morgan law, where you have a union, what do you expect? So obviously you expect that it will become now intersection in between. Okay, so these are the two De Morgan's law that will guide us as we get to look at set theory. Considering a case where you have A complement, union B, and then a complement outside. So we expect the same to apply. So we'll see that where we have A, it will now become just A. Where we have union becomes the intersection, and our B will become its complement. Okay, so I'm applying De Morgan's law to simplify this. But the two De Morgan's laws are the first one and the second one. Those are the two De Morgan's law that they can ask you to state, and of course get to prove. I'll explain later on how we get to confirm, but understand that those are the two De Morgan's laws that you need to understand under set theory. Of course, for the sake of proving, we can look at one example. I'll look at the first one. We have A intersection B complement, right? So we've seen that it gives us A complement union what? B complement. So you can prove this by shading. How? So what does A intersection B mean? So if you have two sets using a Venn diagram, and then this is your A, that is your B, the intersection of B is the region in between there. That's what? That's an intersection. So our label that is A intersection B. Now, A intersection B complement will now be the region outside that. So if you draw the same set, what do you expect? You expect that your A and B, like that. So your complement will be the entire region except A intersection B. That is what you have. Only the region outside A intersection B has been shaded. That is for the left hand side. Now let's look at the right hand side. The right hand side is dealing with A complement union B. So what you do here is, of course, you're considering the two sets again. Okay. So these are set A and B respectively. So it's need for us to deal with. So we've already talked about what, of course, we understand these are inverse sets. We've already talked about what the complement is. It means the set outside the given set. So we'll take our left one to be A complement, the other one to be B complement. And then we'll put a union in between there. What does it mean? So A complement means shade the region outside A. Everything outside A represents A complement. And then the other set we are shading B complement. Everything outside B qualifies to be. So I've shaded the inner. Okay, like that. So now union means that you combine the two regions together. So if you combine whatever we've done in our final result, this is now A and B union. So now we're now saying this is now the union of A complement with B complement. So if you combine the regions together, if you observe these two diagrams, what is going to remain unshaded? So I'll shade first of all A complement. Since union means that you combine them, I'll shade first of all A complement. So what is my A complement? It's the region outside A. That is my A complement. And then I'll shade my B complement outside B. So outside B, So we're noticing that there's only a single region that is unshaded, which is in between, right? Which is A intersection B. So if you look at this, which was now on the right hand side, A complement union B complement, and then A intersection B complement. So we are seeing that the result is what? Is one and the same. So we've proven by shading to say the left hand side is basically equal to the right hand side. Okay? And that has introduced us to the idea of now what? Shading sets. So your last exercise is now, I want you to now to prove the other De Morgan's law, which is A union B complement is equal to A complement intersection B complement. Prove by shading. That is your exercise. Associative laws. Okay. So what exactly are associative laws? So understand what that means. But before that, I'll begin with something so simple, commutative law on set theory. So this is very simple. So you understand that multiplication, addition are commutative, right? A plus B is the same as B plus A. That implies 2 plus 4 is the same as 4 plus 2. That is commutativeness of addition. It applies to multiplication as well. 2 times 4 is the same as 4 times 2. Of course, you understand that 2 minus 4 is not equal to 4 minus 2. So that is that. This is negative 2. That is 2. So negative is not commutative. So commutative laws under sets consider 2 sets. If you say intersection B, it is the same as B intersection A. There is no difference. Okay. So even union, if you say A union B, it is the same as B union A. That is what we are now calling a what? Commutative laws. Okay, very important to understand that. What else do we need to understand? Now, the other thing that we need to understand is I did mention, of course, earlier on in the series to say A minus B is not equal to B minus A. So, of course, subtraction is not commutative. Now, talking about associative laws, which is very important now. So associativeness is more like commutative, except it deals with 3 sets. So if you have A intersection B intersection C, okay. So you understand that mathematically we deal with binary operations. So you only deal with 2 things at a time. You can't find the intersection of A, B, and C at the same time. No. You begin with 2 sets of your choice. So what you begin with is what we put in the brackets. So in this case, we'll begin with B intersection C. Now, these associative laws tells us it doesn't matter what you start with. You can decide to start with the intersection of A and B and then intersect it with C. It is still the same. If you want to remember this easily, think of a case where you're dealing with additions of 3 numbers. You can't add them at the same time. You'd have to begin with 2 numbers first of all. If you have 2 plus 4 plus 7, and then of course the same 2 plus 4 plus 7. You can't add them at the same time. You have to start with 2. So if you start with these 2 numbers, or you start with the first 2 numbers, it is still the same. So what is, in this case you have 2 plus 4 plus 7 is 11. The other side, 6 plus 7. 11 plus 2 is 13. 6 plus 7 is also 13. So you've seen that it doesn't matter what you start with. Remember, Bodmas tells us start with what is in the brackets. So this is basically the argument that is made by associative laws. Very simple and straightforward. So the same concept applies to union. So if you start with a union of B with C, and then unionize with A, it is still the same with starting with A union B and then with union of C. So it's just a matter of understanding the aspect of putting brackets. That is what associative law deals with. So now in terms of proving this, let me try to give you an idea on how you can basically get to deal with this. A union B union C. So let's say we have, okay, let me deal with intersection. I'll give you A intersection B intersection C. Let's say we had the set A made up of even numbers less than 10, 2, 4, 6, 8, and then set P made up of the odd numbers. That is 1, 3, 5, 7, 9. So now this is going to be a very, very bad example. Let me just come up with an imaginary set B, so that we can have 2, 5, 6, 9, right? So at least we have intersection now. So what this means is what I'm having on the left hand side, I'm having set A. So now my set A, I'll write it as it is. We have 2, 4, 6, and 8. So I'll write now intersection. Now we need to find the intersection of B and C. B intersection C now. Now B intersection C is what? B intersection C now requires us to combine the elements between B and C. Now this reminds me that I don't have C in my example. So let's say we have 1, 3, let's say what else? 4, 6, and 9, right? So B intersection C. B intersection C, now a common element between B and C. We have, okay, what do we have? I can see 6 is common and 9 is common. So 6, 9. Is there anything else? No, that's all, 6 and 9. Now, if you look at the two sets, what do we expect to have? The only common element is 6. So that's our answer. So what has dictated our order is the brackets. So on the other side, if you have A intersection B, there's a requirement that I'm supposed to begin with that. So A intersection B, what is common between A and B? I can say 2, 6. And then intersection C. So I'll put my C as it is, 1, 3, 4, 6, and 9, right? And then there the result now is also 6. So what is mattering now is the order of what you basically get to deal with. So usually the way we get to present all this is, you would begin first of all by indicating your left hand side. I'm just trying to show you the formal way of presenting your answer in an assessment. And then you can preferably start with now with what is in the brackets. Show clearly your B intersection C is equal to this. And then on the next stage now you can now continue with A intersection B intersection C. So since you have your A, write your A and then intersect it with the B intersection C that you found there. And then your answer will be found. Then go to the right hand side, do the same. Begin by finding what is in the brackets and then show. That is basically how you get to deal with associative laws. Very, very simple and straightforward. Let's talk about distributive laws. What are the two distributive laws? So I like finding ways and means to make it easier for my students to remember these things. So distributive means you're distributing something, right? So multiplication is an example of distribution when you have brackets. Consider a case where you have x and then you have y plus z in the brackets. So I believe we understand that we can multiply x with y and then we maintain the sign in between and then again multiply x with z, which will be x, z. We understand that simple. So that is distributive law in itself. Okay? So now this means that in a case where you have 2 with maybe let's say 4 plus 7. Okay, let me work with simpler numbers to just make things easier. Let's say 3 plus 4. This is as good as saying 2 times 3. And then again I'll say 2 multiplied by 4. I'm just applying the same concept that I did with the letters there on top. So I can proceed and simplify it. What we have, 3 plus 4 in the brackets is 7. The other side, 2 times 3 is 6. 2 times 4 is 8. 2 times 7 is 14. 6 plus 8 is also 14. So we can clearly see that the distribution is true. Now we can apply this to now set theory. So the basic idea is, what we are trying to consider is,
where we have the x there, there is multiplication there. So you are multiplying x with y and then x with z. Okay. So we apply that now to set theory. So now consider a case where you have an intersection outside and then inside the two sets you have union. So distributive will have a combination of these signs. So we'll consider the one that is outside as multiplication, right? So consider that to be A times B. So intersection has a multiplication. So have A intersection B. Now remember, if we go back to where we had x multiplying with y plus z, we said after you multiply x and y, you maintain the sign in between, which was a plus. So equally you maintain the union in between. And then again we'll go back to what is outside, which is more like a multiplication. A multiplied by c, which is A intersection c. It's as good as that. Opt for that as a opt to remember. Now consider a case where you have a union outside and then an intersection inside. Are you willing to try that one out? Okay, so we'll take our union which is outside as a multiplication. So A multiplied by B, and then we'll maintain the sign that is in between there, which is intersection. And then we'll basically go on and put A union C. So these are the two distributive laws. I've tried explaining using multiplication and addition to help you understand. So it's just a matter of understanding what happens under multiplication, then it will be easy for you to basically get to deal with all this. Okay? So proving or confirming this, in a case where they give you a question, they ask you to confirm, all you'd have to do is begin with your left hand side. Okay? State your left hand side is equal to the A intersection B union C, as we can see. And then of course, remember your board mass tells you start with what is in the bracket. So of course, clearly show that you're finding B union C first of all. And then get to indicate what is in set A. Or what I mean is call back the question, which is now the left hand side. A intersection B union C. And then now show your set A, intersect it with what you had found in B union C, and then show your answer. And then on the right hand side, again do the same. What would just now, you can begin with your A intersection B, and then find A intersection C, and then get to find their union. You get the same answer. That's how basically you get to prove the distributive laws, just like we did under associative laws. Very simple concept, right? Cool. We'll talk about more laws under set theory. Some simple things that you'd just have to understand. Okay, this is just like this is like a game for you. I hope you're enjoying, by the way, what we've done so far, because math is very interesting. So A intersection A. This is as simple as A. When you're intersecting a set with itself, what is common is itself. Not so simple, right? So equally when you say you combine a set with itself, union of a set with itself, it's the set itself. Nothing will change. Okay? So this is as good as you're thinking of a set with two elements, 2 and 3. Whenever you intersect it, whenever you find the union, the answer will still be 2, 3. Okay? So those are called idempotent rows. Okay? The other thing is, look at this. Something interesting as well. If you have a set, and then you're intersecting it with an empty set, what's the answer? What's the answer? Look at set A with an element, with two elements, 2, 3, and then you have an empty set. What's the intersection between the two sets? Is there anything common? So it's an empty set. That's an identity law. You can also think of A being intersected with the universal set. The universal set is made up of everything. So consider a case, I like using a Venn diagram to explain this one. So what do you think first of all is the answer there before I tell you the answer? So if you have set A, set B. And then this is the Venn diagram. Of course, that's a universal set, right? So set A is, this will just actually teach you how you find the union, the intersection of a set. So I'll shade set A. And then I'll draw the other lines now horizontally to shade the universal set. So where the lines are meeting, where the two lines, the horizontal and the vertical, are meeting, that's a point of intersection. So we'll clearly observe that it's only set A that is common, right? Set A is common. So when you are trying to find the intersection between a set and the universal set, the set itself is already part of a universal set, so that is a common point. Okay. Now a case where you're trying to combine any set with a universal set. So the universal set, like I've said, already consists of everything. So A is already part of a universal set. So combining any set with a universal set, you can't get anything greater than the universal set. Okay? You need to understand all that. Is there anything else that I never talked about? So everything else we've talked about. We talked about associative laws and many more laws under set theory. So with this basic introduction, now we can watch the next video now, which is going to talk about some practice questions under what we've covered so far, before you proceed on and learn about set builder notation and set interval notation. Express the following in their simplest form. So basically we have a complement outside the brackets there, so we're supposed to distribute that complement. So the P complement there is going to be what? Is going to be P. So whenever you have a complement of a complement, remember the region complement means outside that given set. So now if you say outside the given set, then again you say outside of it, it is going to be the set itself. So a complement of a complement will cancel out. So a complement of P complement is just going to be P. Then we understand that from De Morgan's laws, we're able to see that the sign changes whenever you distribute a complement. So it's going to be intersection there. Then in the brackets we have Q minus R. So Q minus R is the same as Q intersection what? R complement. Then we'll also distribute the same complement that is outside there to apply to the brackets. Okay. So we've distributed that complement to the brackets, the union, and the P complement. So at this point you can say P intersection. Again you have to distribute that complement. So you distribute it to the Q, it will become Q complement. Then the intersection changes the sign and it becomes what? It becomes the union. R complement becomes R because the complement of a complement. So basically this is the simplest form of that set. X union Y intersection X. So basically this takes us to a distributive law which requires of us to multiply this by that. Of course not really multiplying, but basically that's a basic concept there. So X union Y. So remember when you're multiplying, so that sign is going to be in between. Then again you have the X being multiplied with the X. So this is a distributive law that we talked about. So what do we have? So you have X union Y intersection. So the union of X union X is just X itself. So what we have is X union Y. So let's say this is our X and that is our Y. So X union Y is basically what? It requires you to shade the entire region. That is what your union is. So now intersect that with X. So I'll use a different color to shade for X. So basically I'll shade for X. So where the two different colors are meeting basically gives us the intersection of the two sets there. So in summary what we have is the intersection of X with X union Y. So we know that X is also part of the union of X with Y. So therefore our simplest form is going to be, our answer is just going to be X in this case. Okay, let's move on. For the next one, basically it's also coming from the basic idea of the sets. So how do we get to understand this better? So this is also coming from distributive laws. So this time around we have M what? M intersection. So basically the simplest form of this set is basically M intersection. So it's like we add N union N complement. So this is a distributive law. So if you multiply this with that, it will give you what we have on the left, then by that it will give you what we have on our right. So that is our distributive law. If you're having challenges understanding how we get to understand the distributive law, watch out for, you can check out our other video that shows on how to shade. Basically you understand how to present your work under distributive laws. Okay, so we've simplified it there. So now we're trying to combine N with its complement. So for us to understand that, let me draw a Venn diagram to show an example. So let's say this is our Venn diagram, our universal set. Then in this set we have N. So let me shade N complement. N complement means the region outside what? Outside N. Then I also shade, we have N and also N complement. So I've shaded N complement, then I can also shade N itself. So the union of a set with its complement basically gives you the universal set, because you are interested in both the region itself as well as the region outside. So what we have there is what? Is the intersection. So the universal set is what we have. So M intersection the universal. So you can bear with me, but basically any set that you have is part of a universal set. So intersection of any set with a universal set is basically just the very set. So our simplest form of that is basically M. Okay. The next part, we now have A minus B. What does that mean? So this means we have A minus B is the same as A intersection B complement. So we also understand that, so since we are doing the same there, we are saying A minus B is the same as A intersection what? B complement. So to do away with a minus here, it's going to be A intersection, whatever is in the brackets is going to have a complement outside. Okay, that's what we've done. We've applied the same law that is applying to what is down there. Okay, let's have some space. What do we have? So we now have A intersection. So in the brackets, if you distribute the complement, you have A complement union. So I'm distributing that complement there. So A becomes the complement, the intersection becomes the union, then the B complement of a complement is just going to be a B there. So we have what? We have our B at this point. Okay. Can you simplify it further? We can try it out. So let's try to distribute, since this is let's try to apply our distributive law. We see what we're going to have. So this multiplied by that, we have A intersection A complement. So maintain the union in between. Then again you have the A intersection what? A intersection B. Okay. So A intersection A complement. So what is the intersection between a set and its complement? So unlike the union, which tells us to say what you're going to have is a universal set, for the intersection, if you have set A is basically going to be what is inside there. Then its A complement, its complement is going to be the region outside. So these two things don't intersect. So the intersection of the set and its complement is an empty set. So we have an empty set being unionized with A intersection what? A intersection B. And the union of any set with an empty set is that set. So what you have is A intersection what? B. Okay. We have another set there. So this time around, what do we have? We have A intersection B complement union A minus B. So I'll start first of all by distributing the complement that we have there. So this part which is having a complement will cancel out, so it just be A intersection what? B. The sign there will become the intersection. Then in the brackets we have A minus B. Of course we understand that A minus B is the same as A intersection B complement. So there's a complement that we are distributing there. So we have a complement coming from outside there. So at this point we'll maintain what we have on our left. Then we can distribute the complement to what is inside the brackets. So this A is going to be A complement. The sign will become union. Then again we have B. Okay. So what do we have so far? So we have A intersection B intersection A complement union of B. Okay, so how do we get to simplify it? Are we able to simplify it further beyond that? Okay, are we able to simplify it more? So basically what we can do is retries to shed. We see what we're going to have. So what we have basically is we have A and B. So let's say this is our A, that is our B. So the intersection here is just that region. That is our A intersection B. Then for the other part where we have A complement unionized with B, so that requires us to, let's say that is our A and that is our B. So assuming that is the case that we have, so if this is our A and that is our B, what are we going to have there? So our A complement basically is the region outside your A. So this is your A what? That is your A complement. So unionize it with B, meaning that B is also going to be part of what? It's also going to be part of a set. So that would include this region as well. So we've shaded it. Now we're interested in the intersection of these guys, in the intersection of the two regions. What I've shaded on the left and what I've shaded on the right. So you agree with me that basically what turns out to be the common region is what? Is this part. So the common region is basically just this part. This part is common, which is A intersection of what? A intersection with B. So that becomes our solution. So we have A intersection B as what? As our solution in this case. Okay, so for the other part, we have B complement intersection A union B. So from our distributive law, this is going to be B complement being intersected with A, then union, again B complement intersection B. So we just from saying that, so maintain that we have B complement intersection A. So just from saying that an intersection between a set and its complement is an empty set. Okay, so we have, therefore we have A intersection B complement as our what? As our solution, which is also A minus B. So that's fine, or we can just say B complement intersection A. That is our solution. Okay, going back to the last question, which involves disjoint sets. So I have to emphasize and make a point to say that basically talking about disjoint sets, when you say two sets A and B are disjoint, it means that these sets do not intersect. They do not intersect. So we're going to be working around that to help us simplify or come up with solutions to these sets that we have. So let me draw them down here. So we have our A and what? And our B. So these are disjoint sets. So now looking at the first part of the question, which says A intersection with B. So is there any region where these guys are intersecting? Absolutely not. So therefore A intersection B, there is no intersection, so it's an empty set. We've answered the first part of the question. Then A minus B. So we know that A minus B basically is what? Is A intersection B. Or in other terms, A minus B is A without B. Okay. So unlike in a case where you have an intersection where you get to say you have your A and your B, then you say for your A minus B you only shade this region without, you exclude the intersection. Only part of A is shaded. Now in this time around we're going to shade the entire part of A. Why? Because all of it is without B. So therefore A minus B is the same as what? Is the same as just A, because the entire part of A is without B. Okay, that's how it's different from a set with an intersection. Then what do we have for the other question? So for the other question, we have A complement intersection B. I can even erase this so that we have enough space here. So we have A complement intersection B. So what does it mean when you say A complement? So A complement means you are interested in the region outside what? Outside A. So I'll shade. So this is the entire region outside what? Outside A. So then we are trying to intersect it with B. We are trying to intersect it with what? We are trying to intersect it with B. So I've shaded A complement. Then we are trying to intersect it with B. So basically you are going to see that if you try to intersect it with B, it's what we're going to have is just B, because if I shade my B there, the point of intersection is just set B itself. So A complement intersection B, of course we do understand that it's the same as B intersection what? A complement, which is the same as B minus A. So basically what we're going to have is also just a B as our solution. Then for the other part we have B complements. So we have B complements union A. So this is our B and that is our A. Well, let me start with A. Say this is our A, then that is our B. So for a B complement, it means that we're interested in the region outside what? Outside B for B complement. So for B complement, it's basically this entire region outside B. Then for A complement, I can even use a different color. It's a region outside what? Outside A as well. So at the end of the day, since we have union there, you're going to realize that basically the entire universal set is going to be shaded, because these guys are what? Are disjoint sets. So what we have is just a universal set as our solution. For the other part, we have A union B minus B. A union B minus B. So basically when you talk about A union B, it basically means that you are combining set A with B, which will require you to shade the entire what? The entire region, this region. So that is our A union B. Now we are saying minus B, so you exclude B. So the moment you just remove B, what is going to remain as your answer is what? Is going to be your A. So this marks the end of this video. I just hope that now you're able to apply or simplify different sets that you're given, and you're able to interpret what applies. Let's basically get to discuss the difference between a finite and an infinite set. What exactly is the difference? So finite means countable. You're able to count the number of elements, or you know the exact number of elements of a given set. An infinite set is a set where even if you try to attempt, you cannot count. So uncountable number of elements. Okay, so let's look at some examples. So for countable, you can look at the set in roster form. Let's say 2, 4, 6. Such a set is a finite set because you know the exact number of elements there. So you're able to present a finite set in a Venn diagram. So a Venn diagram is something like that. Okay, so you're able to present such a set there. Okay, because you know the number of elements are limited, so they're able to fit in. But for the other side, you cannot. So examples of an infinite set would be, consider a case where we have 0, 1, 2, and then I'll put dots there showing that there are more elements coming after. Okay. Another example would be even from starts as well. You may have dots from the start, and then you can have 0, 1, 2. So you're able to see that despite it ending on the right hand side, it is uncountable going to the left. Because looking at the trend there, we've got 0, 1, 2, those are integers. So even negatives don't end. So that is also an infinite set. Now let's end with two interesting examples. Consider a case where you have 0, 1, 2, and then for argument's sake, I can even say 1000. And then consider a case where you have an empty set. Are these two sets finite or infinite? Starting with the first one. So we don't know, we know the way the set is moving, right? Now the fact that there is something like that shows that there are elements that are missing in between. Now the fact is we know the starting point and the ending point. So that tells us this is a finite set. We know the number of elements there. Okay, we're able to count because we know the starting and the ending. Whether it's a big number, 10,000, provided you know the beginning and the end, it is a finite set. Now, what if you look at an empty set? Is it a finite or an infinite set? Do we know how many elements are there? Or we don't? So it is a finite set because we know it has got 0 elements or members. Okay. So that is exactly the difference between a finite set and an infinite set. Next time, if you associate on that, be able to identify which one is a finite and which one is not. Okay, have you ever heard of disjoint sets? Okay, so by simple definition, we can just say disjoint sets are sets that do not share any elements. In other terms, you can say there is no intersection. Okay, so intersection of disjoint sets is an empty set. So if you have set A, for the sake of examples, having members 0, 1, 2, 3, set B, having members 4, 5, 6. So we can clearly see that these do not have any intersection. So if you are to ask to find the intersection of A and B, it is an empty set, as we saw the symbol of an empty set, or even just like that. So such a case, we can call A and B as disjoint sets. So how do you get to present that in a Venn diagram? So in a Venn diagram, if you have something like this, A and B, you've seen that I'm not showing any intersection there. There is no intersection between the two sets. So the two sets are referred to as disjoint sets, as simple as that is. There is nothing more, nothing less. That's what disjoint sets are. In this video, we're just going to understand how you basically get to go about describing the shaded region of a Venn diagram. Of course, we understand the box itself, we call it the universal set. Okay, we can use either capital letter E or capital letter U. It's still one and the same. Okay, so I will start with a very simple example, as you can see. So if you look at the diagram that we have on display, you'll see that the entire part of A and B have been what? Have been shaded. So it's a try and error thing. That's one thing that I've noticed there. And since these are the only parts that have been shaded and they've been shaded completely, I understand that it was just a combination of A with B. So to me that is A union with B. That is the region that we've shaded. And it is true, if you give somebody to shade that region where you have A, B, and C, that's the region they're going to shade. Now, we are now advancing and trying to just be a bit more complicated. Look at what we have now. Now this is a bit unique and interesting. So let's try to notice what we have. Of course, our region of focus in this case would be C. Now let's try to notice a region that has not been shaded. So this is, so C has not been shaded, as we can see. Now is it the entire C? No. So now we can see that the region that is part of B has been shaded, right? That region that is part of B has been shaded, despite it being part of C. So how best can we describe this region? How best can we describe the region that has been shaded? So I believe the best way I can start this is, since first of all we've shaded outside C, I can say C complement. Now if you say C complement, you're only shading the region outside what? Outside C. So that is going to exclude this region because it is part of C. Now how do we basically get to include that region that is part of B? Now we understand that that region is the intersection between B and C. So I think we can just combine to say C complement, the region outside C, combined using a union with what? That other region, this inner region that has been shaded as well, this one, which is part of C, is the intersection between A and C. So say A intersection, it's not A, it is B. So the intersection between B and C combined with the complement of C is a shaded region. I feel that is the way you can describe that region. If you've got a better way, you can basically comment in the section. Okay, two more to deal with. Now I've got my Venn diagram there. Consider a case where we only shade this region. That region is the intersection between A and B. Now if you shade that region, I've already told you the answer, right? That's an intersection between A and B. That's the answer already, straight away. Okay, let me shade something more unique. Let's consider where we shade just C. We've shaded C, right? How do we describe that region? Now notice that the entire C has not been shaded. There is this part that has been excluded. So that's why we'd have to be now smart about it. So how best can we describe this region that has been shaded? Remember, there is this part which is part of C but has not been shaded. So if you try to assess this region which is part of C and has not been shaded, it is the intersection with A. So that region is A intersection what? C. It has not been shaded. So in describing the region, you say, first of all, we understand we've shaded C. Now, we are removing which part? We are removing that region. So removing, to me, I feel it's subtraction. So I can just say C minus the intersection with what? With C. A intersection C has been removed. Now, that looks too complicated somehow. How best can we describe it? What if you said C without A? Isn't that more simpler? C minus A. So every part that is of A, you remove it. That is still fine, right? So C minus A is more simpler and straightforward, which is the same as C intersection A complement. The region outside A combined with the region of C their intersection point. That is what you get to shade. So I feel this is an introduction that you can utilize to when it comes to the shading or presenting of sets on a Venn diagram. Okay. So in the next video, you basically get to learn how you get to do the opposite, where they give you what to shade, and then you basically get to shade on your Venn diagrams. We've been given a Venn diagram, then we're required to shade A intersection B and many more questions. So we'll start with that. So we have our A intersection B there. So what does that mean? That requires us to shade the region that is common between A and B. So if you are to shade that region, what you're going to have is this part, because that is the region that is part of both A and what? And B. So you look at the point where they are intersecting. So basically this is their intersection point, because this region is part of B, it's also part of what? It's also part of A. Okay, so that is how you get to answer the first one. Then moving on to the second part of the question, it is requiring us to shade A intersection B union C. So I'll write that A intersection B union C. So whenever you're simplifying a set, basically the simplest way of approaching it is by starting with what's in the brackets. So if you look at what's in the brackets there, we are trying to combine B together with what? Together with C. So I'll shade the entire region of B union C. So it would require us to shade the entire region of B. So that is our B. Then we also shade what? The region that is part of C. That's what it means when we say union of B and C. Okay. So now we have our B union C. So we need to find the intersection with A. So let's try to shade A now. I'll use a different color so that we see where they're going to be intersecting. I'll use a blue. So if you shade A, this is A. Okay. So we shaded A. So now if you look at this, we are trying to find the intersection between B union C, which we've shaded in yellow, then A, which we've shaded in blue. So the point of intersection, meaning that where you can see both colors, that is our region that we're supposed to shade. So in summary, if you are to draw this, what you're going to have is something like that. You have A, B, and what? And our C. So I'll write that is our A, that is our B, and our C. So what region is having both colors? So if you look at the diagram that we have, it's basically this region. Okay. So you can even shade it. So it's basically this region. The region part of A, which is also part of B union C. That is the intersection region. So basically that is what you're supposed to shade. Okay, let's move on to the third one. So if you look at the third part, it is C minus A intersection B. That is our third question. So we have C minus A intersection B. So we need to understand that this is the same as what? Remember we said if you have A minus B, basically this is equivalent to A intersection B complement, because you're trying to talk about the region that is part of A and not in what? Not part of B. So you exclude the intersection of the two. So C minus A intersection B is basically going to be C intersection A intersection B what? Complement. If you want to understand it better, what we can do is we can shade it. So if we have the three sets A, B, and C, okay, let's say that's what we have. So we have our A, we have our B, we then have our C there. Okay, so C minus A intersection B, it means that we are interested in the region that is part of C. And what is our C in this case? What region is part of C? So this is the region that is part of C. This is the entire region of C. Now we are trying to exclude the part that is part of the intersection of B, A and B. So which one is the intersection of A and B? So the intersection region is this one. So we exclude that part. That is the region that we are excluding. So what we are going to remain with is basically just this part, because we're looking at the part of C excluding A intersection B. So the intersection is what I've shaded in red. So the green part is what we are interested in. So if you want to present it in a different way, you can also say basically it's region of C intersection with what? The region outside A intersection B complement. So if you talk about A intersection B complement, it's the region outside the red part. So this is A intersection B complement. So now we want to find the intersection with C, which will still come out to be what? This region that we've shaded in green. Okay, so that is why we're saying this is equivalent to that part. So now let's try to represent it on the Venn diagram. In summary, what we've said. So basically what we have is, in fact, I've actually even answered the question. Let me just show what I did. So what we have is, we are saying we have our A, we have our B, and our C. So when we say C minus A intersection B, it means that the region of C without the intersection of A and B. And remember we've said for our intersection is basically the intersection of A and B is this region. So we are excluding that from C, meaning that what we are going to remain with is the region that I'm going to shade in a different color here. So what we are going to remain with is this part. We are only excluding the intersection of what? A and B. Okay. So you've shaded C minus A intersection B. Okay. So that is how you approach it. If you want, you can also change a form. You approach it using that form where you say shade C, then intersect it with A intersection B complement. You're still going to come up with the same solution for that part. Let's try to move on. Let's try to look at the fourth one. We see what we're going to shade. So if you look at B minus C, this one is direct. This one is straightforward. So looking at this kind of Venn diagram where we have A, B, and C in such a way, you have your A, you have your B, and your C. So B minus C means a region of B without what? Without C. So we are required to shade B without C. So we're only going to shade the region of B without C. So remember, this is a part of this is part of C. So we are going to exclude it. We are going to exclude this part, which is C. We are only interested in the region of B without it. So what we are going to shade is the entire region of B except the region of B, which is also part of C, because it's saying B minus C. Okay, that's easy. That's easy. So what about if you said C minus B? When they say C minus B, it requires you to shade the region part of C, excluding that which is part of B. Okay, because we are saying that is basically C intersection what? B complement, meaning that you're only interested in the region that is part of C and outside your B. Okay, so we are on this one. So we have A intersection, B intersection. In this video, I'm just going to introduce you to set builder notation. So what is set builder notation? So set builder notation is basically just a mathematical shorthand notation of presenting a set. So when you look at this, I'll just explain what they mean. So this symbol, we learned that it stands for a member of. So I'm trying to say X is a member of. Now this symbol Z, it stands for integers. So you know that we have integers, know that we have real numbers, know that we have rational numbers, denoted as Q. Yeah, and of course the other kinds of numbers. So there's a video you're supposed to watch after this, which will deal with sets of numbers. You understand all the different kinds of sets that are there for your assistance with the progress. So now this other symbol that you're seeing there, which is like a line, that is denotes, it's just the same as such that. So in some textbooks, or it's also okay for you to say X is a member of integers, and then you search that -2 is less than or equal to X less than or equal to 3. I believe you're okay with these brackets are curly brackets. So they can ask you to list the elements of, if they've given you set builder notation, or they can ask you to describe or they can ask you the other way around, which is they give you a list and then they ask you to write inside builder notation. So in this case, if they ask me to list, I know what integers are. Integers are negative and positive numbers. So they are saying -2 is less than or equal to X. So -2 -1, 0, 1, 2. I'm ending at 2 because it is less than 3, not less than or equal to 3. So that is how you get to deal with set builder notation. Now, giving you another example, consider a case where you have the same kind of a set. Now, let's say you have, let's say 2, 4, 6, 8. So if we end there, are you able to describe these? So we're able to see that, first of all, x is, these numbers that are there are what? Are even numbers. Okay? We understand what even numbers are. What else can we see? We can see that these numbers are less than what? They are less than 10. So we'll say x is a member of even numbers. There's no symbol for even numbers that I know of. So such that x should also be less than 10. So these two conditions basically describe the numbers that we have there. Even numbers, and then these even numbers are less than 10. So this is set builder notation. Okay? Many things apply. So you can watch the next video now, which now has got about more than 6 examples on the same to help you understand. And of course, the video will be a summary of everything you've learned so far. After watching the next video, you can now feel free to attempt the practice questions on set theory to just test your understanding. And if you have any questions, feel free to get in touch with our tutors.
C complement, there. So how do you get to shade this one? So what you can do is you can try to simplify what you have first of all. So you have A intersection. So from De Morgan's law, this can become, you distribute the complement, you're going to have B complement union C. So a complement of a complement is basically what? They'll cancel out. The intersection becomes the union, then the B becomes the complement. So basically that is the simplified form of the statement that we have. So let's try to shade that. So looking at the sets that we have our A, we have our B, we also have our what? Our C there. So you have your A, you have your B, and your C. So you want to shade the intersection of A with B complement union C. So the approach that we're trying to use is first of all by shading A, then you come and shade. So let's start with first of all with what's in the brackets. Let's shade B complement combined with C. So B complement, we're interested in the region outside what? We're interested in the region outside B. Let me even put the Venn diagram around. Okay, so that's what we have there. So now, this is our inverse set, by the way. This is our inverse set. So now what are we trying to do? We're trying to shade B complement union C. So which one is our B complement? It's a region outside B. So I'll use a different color for that. I'll use I can use red for B complement. So B complement, region outside B. So every part outside B. So not outside B. So notice that I'm not shading anything within B. I'm just shading outside B. So now it's supposed to be combined. So union tells you to say combine. So I can continue by shading every region that is part of C. I can even use I'll use the same color since it's the same set. B complement union C. So I'll shade every entire part of C. So this is going to include a certain part of B. Okay. So that region is shaded. Why is it shaded? It is shaded because it is part of C. We are saying the union. Okay, so we have B complement unionized with C. That's what we have. The entire region that we've shaded. This is all B complement unionized with C. So now we need to find its intersection with A. So let's shade A. I can use green for A. So this is our A. Okay. So now our solution is going to be where you are seeing both green and red. And what region is that? So it's basically this region. Okay, so that's the region that we are interested in. So what is the region that we are interested in? And we can even shade it. So let's try to come up with our separate Venn diagram somewhere. Surround. So what we have is, we are saying we have our A, we have our B, we also have our C there. So we have our A, our B, and our C. So what region is shaded? It's only this region. Okay. This region is also shaded. Even this part is shaded. Okay. So it's only a small part of the A which is not shaded. So basically, that is our solution there. The other approach that you can use is by looking at it as you have your A. You're trying to find its intersection with B intersection C complement. So what would you say? You know that what is in the brackets there. Let's try to use that approach. We try to see what we're going to have. So we have our A intersection B. So B intersection C complement, if you can remember, is what? It's the same as B minus what? B minus C complement. So what is your B minus C? Basically, if you talk about B minus C, you're trying to talk about the region what? What region are you talking about? The region of B without what? Without C. So if you have this part, your A, your B, and your C. So what region of B minus C do we have in this case? So the region of B without C means that you exclude this part of C, exclude it, then you only shade the remaining part of B. But then that's not the region that we are interested. So if we are going to shade B minus C, we are going to shade this part. Okay, that is our B minus C in this case. Now we are not interested in B minus C, we are interested in what? In its complement. So what does it mean? We're supposed to shade the region outside that. So let's try to shade outside that part because we are interested in its complement. So what we're going to have is this outside that. So this part. So we're not only going to shade B minus C because we're interested in what? In its complement. Okay. So now we are trying to intersect it with what? We're intersecting it with our A. So let's shade A. So if you shade your A, so now I said where the lines are meeting, basically that's where you have your A. So equally you've seen that it's only this part of A that is excluded. Only this region is excluded. So basically we're going to shade this region, which is going to give us what we have on our right. So whichever method you work with, you're still going to have the same solution. Okay. Let's try to look at the final one. So for the final part of the question, what we have is we have A complement intersection B minus C. So this one is straightforward. We can just draw what we have. So we have A, we have our B, and we have our C there. So this is our A, that is our B, and that is our C. If you want, you can even draw. Okay. So this is our universal set. So we're trying to shade B minus C. So I will shade B minus C using a different color. So for B minus C, it means region of B without C. So remember, this entire region is part of C. So we are trying to exclude it from B. So our B minus C is just going to be that region of B without what? Without C. Then for our complement, we're going to use a different color, meaning that we're interested in the region outside what? Outside A. So we're not going to shade in A, we're only going to shade outside it. Let me even use a green there. Okay. So outside A. So notice that this region outside A is this part. Okay, because this is where our A is passing. So outside that, that is what we are going to what? To shade. Okay. So now, where exactly are the colors meeting? So if you look at where they are meeting, it's basically which part? So it's basically this part. This is where these lines are what? Are meeting. So that is our region of our interest. The region that is outside A and part of B minus what? B minus C. So in summary, what we're saying is it's this part. If you try to show it clearly, what you have is so if you look at the approach that I've been working with, it requires you to have a draft, then you get to have your final solution that your lecturer is in need of. So it's basically just this part, and that is your shading. Okay, so that's it.
Okay, so I basically do understand. In the previous video, we were told to watch a video which is going to be like a summary of everything, but before that, there is need for you to watch set interval notation. So just a few basics that I'll introduce to you. So set interval notation deals with you presenting a set on a number line. Okay, so the notation that you basically expect to familiarize yourself with under this part is an aspect of you presenting a set on a number line. Okay, so let's basically get to look at an example. So consider a case where you have a number line like that, and then you have 0 and 10. So I can present a set like that. So the other way I can present such a set is by saying 0, 10, using those brackets. Now, when I shade a side, it changes. The bracket becomes that. It becomes 0 all the way up to what? Up to 10. The other side will remain the same. So you now understand what these brackets, the difference between them, right? That's what set interval notation tells us. So in other terms, the other thing that you have to understand is set interval notation represents real numbers. So real numbers, basically you understand that it is a set of both rational and irrational numbers. So we understand that the elements between 0 and 10 are uncountable. So if you have such a set, it means 0 and 10 are not members of the set. Now in this other one, it means 0 is a member, but 10 is not. But all the elements between the two, or all the real numbers between the two, are members of a set. Okay. So under set interval notation, they expect you to be able to present a set on a number line, as well as present it using this notation. Okay. So with that understanding, you can watch now the full video about set interval notation, and from there now you can watch a video summarizing the entire set theory topic. Okay, from there now you can answer the questions.
Have you ever seen a set being represented on a number line? And do you basically understand what it means when you look at such a set? So here with me I've got a diagram that is demonstrating what we are going to talk about in this video. So there are some cases where it is shaded, some cases the endpoints are not shaded as demonstrated there. So basically we call this set interval notation. So set interval notation basically deals with a study of real numbers. So you need to understand what real numbers are for you to be able to understand the important idea. So we have what we call infinite set. So an infinite set is a set that has got unlimited elements or members. You're not able to list them. A finite set, which we basically represent using what we call the roster form, where you get to list the members of a given set in that form, for example. That is an example of a roster form. Of course, even under roster, you can also represent and also unlimited. For example, I can put dots there. It becomes infinite. But in most of the cases, we get to deal with a study of real numbers. That's when we basically work with set interval notation. So this is called roster form. Now, think of a case where you're trying to think of real numbers between 1 and 2. So if I ask you to list the real numbers between 1 and 2, one thing that you need to understand is there is unlimited numbers between 1 and 2 in terms of real numbers. So a number like 1.1, a number like 1.0, a number like 1.001. Notice that I'm coming up with a lot of numbers that you didn't even think about in terms of the numbers between 1 and 2. So what we are saying is we have unlimited, because somebody may decide to say 1.000, add a lot of zeros, 1. So
Now let me ask you a very interesting question. What number comes immediately after 1 that lies between 1 and 2? I know some of you may say 1.1, but what if I say 1.01? Again, somebody may say 1.001. Somebody may continue adding zeros before the 1 there. So we basically don't know. That's why we now use set interval notation to represent our understanding of infinite set that deals with real numbers. Okay, so now let's try to understand the notation that we basically work with when dealing with set interval notation. So looking at what we have, okay, so think of a set where we have a set between 1 and 2. Now, the interesting fact about this set is going to be 1 and 2 are not supposed to be part of a set. You think of that. Imagine 1 and 2 are not part of a set. So that would mean we don't have to shade the endpoints just like it is. So this set A is going to be 1 and 2. So now notice the kind of brackets that I'm using. I'm using the curved brackets. Okay, so I'm using the curved brackets. So curved brackets are used to indicate when the endpoints are not shaded or when the end numbers are not part of a set. So in this case, what it means is set A involves or consists of numbers between 1 and 2, where 1 and 2 are not included. Let me decide to change something about it. What if I put such a bracket on that end? So what kind of a bracket would require me to shade at the end point where we have a 2? And that indicates or tells us to say set A is made up of numbers after 1, including 2. Now 1 is not a member of set A, yet 2 is a member. That's the difference there. Okay, so we now know what it means when we've shaded and how we basically get to represent that. Now assume they wanted us to find the complement of set A. So that would require me to draw again on top. Now in this case, we'll assume our inverse set consisted of numbers from 0 to 10, where both 0 and 10 are included. So that would mean that we know that a complement of a set is made up of elements outside that given set, but within the inverse set. So what numbers are, or what elements are outside A, but within the range 0 and 10? So we have a 0 this side, and then after 2 we need to make sure we end up where we have what? Where we have a 10. So we've shown the entire inverse set. So the complement is going to move from 2 up to 10, and then from 1 up to 0. Now notice that the endpoints, according to the inverse set, we have these brackets which indicate that 0 and 10 are part of a set. So we'd have to shade the endpoints. Now the points that are attaching to our set A, we said when we've not shaded the endpoint, for example at 1, we've not shaded that part. That tells us to say 1 is not part of A. So whenever an element is not part of a given set but it is part of the inverse set, it is supposed to be part of a complement. So we would have to shade 1, meaning that 1 is part of a complement since it is not part of A. And then the opposite is true. If you check here, 2 is part of set A, so it cannot be part of its complement. So a complement will not have 2. Now how do we get to present our answer in this case? So our answer becomes a complement from the left side. 0 is shaded, so say 0. So I'll use this kind of brackets, 0 all the way up to 1. Now notice that 1 is also what? Shaded. Now there is a gap in between the complements, so I'd have to use a union to combine them. And then we're starting from 2. 2 is not shaded, all the way up to 10. 10 is shaded. So basically that's how you present our solution. Okay, that's how we basically get to present our solution using intervals. Now with that understanding, we know what a complement is and we know what a set is. So now look at the initial diagram that we had from start. So I want you to pause the video and now try to represent our sets A and B. So looking at set A is moving from -4 up to 2. So looking at -4, the endpoint is shaded. So are we supposed to use this kind of a bracket or a curved? So use this kind of a bracket to show that -4 is part of the set. All the way up to what? All the way up to 2. Now, are we shading 2? 2 is not shaded. So what kind of bracket are we going to use? We'll use a curved bracket. That is, this is our set A. So we say A is equal to that. Now our set B is moving from where? Is moving from -1 all the way up to 4. So -1 will be shaded because of what we're able to see, and then 4 will not be shaded because it is not shaded, so we'll use a curved bracket. So I believe we now understand how when we use a curved bracket and when we don't use it. So with that understanding, let's try to find now, for the sake of examples, let's try to find the intersection A and B. Now, unlike the other example that we considered, in this case, let's consider our universal set to be real numbers. So real numbers means we are moving from -infinity to +infinity, from affinity to infinity. Okay. We'll start first of all by finding the intersection of A and B. So when we are talking about the intersection of A and B on a number line, it is very important, even when they have not drawn for you a number line, I would advise you that you get to basically to do it for yourself. So in this case, assume we are given what I'm from erasing there, and then we drew our number line. Now want to find our intersection. So we can find our intersection by drawing the region that overlaps the two sets. So if I shade this region, this is the region that is overlapping between the two sets. It is the region that is common between A and B, as we can clearly see. Okay. So from here up to that point, that is the only region common between A and B. So we are considering the region in between. So we'll notice first of all we are starting from -1 up to 2. Interesting. Now, how do we know what we're supposed to shade at the endpoints? The first thing I'm going to ask you is, when you look at what we have, consider -1. Is -1 part of A? We can say yes, because it is between -4 and 2, because we know that our set A is moving from -4 all the way up to 2, and then -1 is between -4 and 2. So we can say -1 is part of A. Now, is it part of B? So at the endpoint -1, set B is shaded, so it indicates to say it is also part of B. So since it is part of both A and B, it is part of the intersection since it is common. So we'll use this kind of a bracket. Now, we'll check 2. The first question is 2 part of set A? Set A is moving from -4 to 2. Now at 2, we can clearly see that it is not shaded. So it implies that 2 is not part of set A, since at the endpoint 2, A is not shaded, so it is not part of the set. So therefore, A does not have 2. So 2 is not a member of what? A. What about B? So notice that 2 lies between -1 and 4. So 2 is a member of what? 2 is a member of B. But it is not part of A. So it is not part of the intersection. Why? Because it is not in A. Intersection involves elements that are part of both sets or all the sets indicated. So we'd have to use a curved one, implying that our intersection moves from -1 all the way up to 2, but 2 is not included since it is not common. It is not part of set A. Okay. And assume this kind of a same question, they ask you to find the complement, where they give you A intersection B in brackets, and then they ask you to find the complement of it. So you know that I can even erase. Okay, before we consider such a question, okay, let's consider it. So notice that we found our A intersection B to be from -1 to 2, and then we said our answer was -1 to 2. So -1 is shaded, 2 is not shaded. So if this is our A intersection B, now they want us to find the complement of it. So we'd have to start from here going this side, and from this side going the other side. Now we have to observe something. Observe that -1 is shaded. So -1 is part of A intersection B. It cannot be part of A intersection B complement. So we'll leave it as it is, unshaded. On the other side, we can clearly see to say 2 is not shaded, so we can shade the complement. So the way it is, if you look at the set, if you have set A, whatever is in the A complement is what is outside. It cannot be inside and outside. So that's why we are saying if it is shaded, it cannot be shaded on the other side. So it's like you basically get to do the opposite. So if a set itself is shaded, the complement is not supposed to be shaded, and that's basically what we are observing. The set is not shaded, the complement is shaded. The set was shaded, the complement was not shaded. Now, observe at the endpoints I'm putting arrows there. Why? Because in this case, we don't know where the universal set is ending. We are using infinity and affinity. Now, in all cases, infinity and affinity should never be part of a set. So therefore, say, this representation or this A intersection B complement going to our left hand side is moving from -1, and -1 is not shaded. So I'll use a curved bracket all the way up to -infinity, and I've said -infinity will never be part of the set. Now we'll use union to combine the other side. The other side is starting from a 2, and we've shaded it, so we'll have to say 2 all the way up to +infinity, because our universal set in this case is a set of real numbers. In the other case, we add our universal set ending up to 10. That's why we had to put 10. In this case, it is a universal set, is a set of real numbers. Okay. So basically, those are basically the simple ideas that I would want you to know. And I think one more thing that I would want to highlight is how we basically gets to handle the union of a set. Okay. So remember our set A moved from -4 to 2, and then we have another one from -1 all the way up to 4. So this part shaded, this part shaded. This is our A, that is our B. How do you get to find A union B first of all? That's the last part of the question we're handling. So the way you get to handle it is, in a case where you have an intersection, there's an overlapping region, just get the endpoints. So in this case, we'll consider from -4 all the way up to 4. Our answer becomes -4 all the way up to 4. Now we'll consider the endpoints. This endpoint is shaded, so we'll use this kind of bracket. That endpoint is not shaded, we'll use a curved, since it is not shaded. That is how we get to under the union of sets on a number line. Now think of a different case where we get to where there is no overlapping. Okay. Assume this one is ending here. Maybe for interesting sake, I can even put something like this. So if I give you such sets A and B, do you think there's any intersection there? Notice that -1 is not part of A, and then it is also not part of B. So in this case, there is no intersection. There can only be an intersection if both ends are shaded. That's when you can have an intersection. Now, that is not our interest there. Now, imagine our set B was ending at 2. And then they want us to find the union of two sets. This is what is very important for you to understand how we get to handle that. So our set, there's no intersection here, so we cannot just get endpoints, because that would include the region that is missing, but there's a region that is missing. So in such a case, the region that is missing, we basically get to put a union in between. So our answer will just be Set A is moving from -4, where -4 is shaded, up to -1, where -1 is not shaded. So combine that using the union, and then 2 is shaded all the way up to 4. 4 is not shaded. So this is a representation of a case where there's a gap, where there's no intersection, how you get to represent the union. And basically you've noticed this because this is basically what we are using when we are dealing with a case where we are finding the complements of a set, where we say the complement is going this side and the complement is going this side. So we use a union to combine the two sides. And that is basically the main idea that lies behind set interval notation.
In this video, we're going to go over more practice questions on set theory. We're going to go over moving from set builder notation to listing the elements and vice versa. So there's some questions that are going to require us to move from set builder notation and get to roster form. There's some questions that require us to state whether they are empty by looking at the set builder notation. So being able to identify singletons, being able to identify finite and infinite sets, and being able to write down the power sets of given sets, and also being able to perform basic operations on a set, and lastly set interval notation. So let's get started. Okay, first question says write the following in set builder form. So we've been given a list of elements in various sets. So for example, if you look at set A, we've been told we have 4, 8, 12 and 16 as the elements in that set. So now, what is set builder notation or set builder form? So for a set builder notation, it requires you to summarize or give it in a different way. Instead of you listing the elements, you just kind of describe the elements that are there. So for example, in this case, we're going to say set A. So we'll consider the elements there to be represented by x, and therefore we can say that x is such that x. So if you look at 4, 8, 12 and 16, to what class of numbers, or what numbers are they? How would you describe them? So x is a member of what? So x is basically an even number. We've seen that what we have are even numbers, okay? So x is an even number. Then not only is it an even number, it is limited, because if you leave it general to say an even number, that would mean that even 2, 18, numbers outside the given range are also part of what? Are also part of the possible solutions. But in this case, we want to restrict it to move from 4 to 16. So I can also say x. So I can say 4 is basically less than or equal to x. Then x is less than or equal to 16, meaning that we can't go beyond that. In other terms, you can also say, instead of writing is an even number, you can just say x is, you use that symbol for a member. Is a member of what? Even numbers. Okay. So it's all one and the same. So that is what set builder notation comes out like. Then moving on to set B. For set B, we have numbers 3, 9, 27, 81, 243. So basically, what is that all about? How do we get to describe that? What sets of numbers do we have? Okay. What set of numbers do we have? So if you look at this one, what is basically guiding us here, the guiding principle is that we have numbers 3, 9, 27, 81. So there is no way we can say, no, it is a set of odd numbers. Because the moment you just say odd numbers, we are going to include all the numbers that are not divisible by what? That are not divisible by 2. And that would include numbers like 7 that are missing there, 7, 11. But in this case, it's kind of a trend that is moving, okay? So if you try to study what we have, basically if you get to study the numbers that we have, it's like there's an equation that is defining them.
So for example, if you get to try 3 to the power n, if you try 3 to the power 1, it will be 3. You try to the power 2, it will be 9. Try to the power 3, it will be 27. The power 4 is going to be 81. To the power 5 is going to be 243. So it's like there is an equation that is kind of defining that. So what are we going to say? We are therefore going to say that x is such that x is equal to what? 3 to the power n. But what else do we know? Apart from knowing that our x is defined by that equation, we are also aware that what is n? N is what? N is focusing on what? So n is focused on natural numbers. We are putting in natural numbers. So n is a member of what? N is a member of natural numbers. Okay. So the power that we're going to be putting there should be a natural number. Then the natural numbers are also restricted to what? So just from natural numbers should be less than what? So we've moved from 1, 2, 3, 4, and 5. So natural numbers less than what? Less than or equal to 5. So we've restricted our set builder notation to that. So x is given by 3 to the power n, where n is a member of natural numbers and n is less than or equal to what? Or equal to 5. Okay. That is the way we are approaching this question. So we've described the given set there using set builder notation. Let's try to move on to the third one there, where we've been given our C. So what are we able to see at that point? So we have 2, 4, 6. 2, 4, 6. So in this case, what do we have? We are starting from the minimum even number going up. So what can you say? We can therefore say that x is such that x is what? Is an even number. So not only is x an even number, it's including even numbers that are what? That are greater than what? No, we can just say it's general, because if you look at 2 is like the minimum there. Okay, so what can we say? What are we saying about the even numbers? So x is such that x is an even number. Then the minimum that we have as our even number, of course, we do understand is our 2. Okay, so even where you just say, even where you leave it empty without even putting the range, it will still be correct, because wow, look at this. What are we able to see there? We're able to see that we are starting from a minimum even number and we're going up, meaning that we are not restricted. It's just like moving up. So x is an even number, of course. Okay, so if you want, you can also say x is of course greater than or equal to 2. Yeah, there's basically no difference there, but I don't see any necessity of us doing that. Okay, so now we had moved from the roster form in the first question and went to set builder notation. Now in this case, we're going to reverse what we have. We're going to take this to we've been given in set builder notation. Let's take this to roster form now, where it gets to list the elements. So I'll start with the first one there. So our A, the statement is saying is x is such that x is the letter of the word mwana wasa. I don't know how you read that word, but basically we've been told x is the letter of that word. Okay, so now what is our goal here? Our goal is to list the letters. We are listing them in roster form, so we're just going to list the elements. So we have A, we have W, so what else? We have N, we have S. So I can start for our person, I start with A. Then I can go to M, I can go to N, I can go to then W. I think all the letters are done. Yeah. So there's no need for me to repeat A, because there's no way. Why should I repeat it? Because it's the same element, it's the same member. So I think these are the enough letters that can come up, because if we're trying to write that, we get the first letter M, we go by that one, we come back to our A, we go to our N, we go back to our A, then we go back to that A. Just so from all just these letters, just 5 letters, we're able to come up with that word. So we've listed our set there. Then moving on to the second one, set B. So for this one, we are saying x is such that x is a factor of 20. So what is a factor of 20? So a factor of 20 is any number that you are able to divide into 20. So x is such that x is a factor of 20. So you can list the elements that are, or the members that we're able to do the factors of 20. So what are they? 1 itself is a factor, 2 is a factor, 4 is a factor, 5 is a factor. What else is a factor of 20? What else do you know as a factor of 20? 10 is a factor, then 20 itself is also a factor. So these are the factors of 20. X is such that x is a factor of 20. Okay. So there's no restriction. It's just general, a factor of 20. If I said maybe a factor of 20 less than 20, 20 would have not been part of a solution set. But in this case, it is just open. So we'll just write whatever we can. Then for C, x is a root of x squared minus 4x. X is a root of x squared minus, so let me create some space here. So what is a root? You need to understand what a root is. So x squared minus 4x is equivalent to 0. And what do they want? They want a root of that equation. So basically you need to understand that roots are basically the points in which a graph gets to cut the x-axis. So these are referred to as the roots, and they get to occur when y is equivalent to what? When y is equivalent to 0. So that's what we need to understand. So in such a case, it requires us to solve the quadratic equation using any method possible. So in this case, I can just like factorize it. Since I don't have a constant, I can just factorize. Then I'll remain with x minus 4 equal to 0. So the first value is x is equal to 0. The other one is x is equal to 4. So these are the members that I have. So I just have 0 and 4. These are the only roots that we can have for that equation. So we just expect to have two members in our set C. Moving to set D, we are told x is an integer. Then it's moving from negative 3 over 2 all the way up to 11 over 2. So approximately, what is negative 3 over 2? What is negative 3 over 2 in terms of a decimal? It's negative 1.5. So it's like we're moving from negative 1.5 all the way up to 11 over 2 is the same as 5.2. Sorry, 5.5. 11 divided by 2. It's 5.5. So now, what are integers? Before we get to list them, we need to understand what integers are. So integers basically consist of natural numbers, okay, and also negative numbers. So we just consider all numbers. We don't consider decimal numbers or fractions when we are talking about a set of integers. That's what you need to understand. So despite them telling us from negative 3 over 2 up to 11 over 2, we are not going to consider them. Okay. We're not going to consider fractions. We just consider these numbers that are in between the integers themselves. So negative 1.5 is somewhere there. Then 5.5 is slightly just after 5. So these are the possible members of that set. These are the integers that are between negative 3 over 2 and 11 over 2. And therefore would restart to be our set what? D. So it is a requirement that if you want to be getting things right, you need to understand sets of numbers. You need to understand what rational numbers are, irrational numbers, real numbers, complex numbers, you need to understand them and you need to be able to identify them, because they're very, very applicable as you get to look at your sets. Okay, we do have another one there. So for this one, they are saying x is such that x is equal to, so I'll write that better, n squared minus 1 divided by n squared plus 1. So now, we are told n is a member of natural numbers. Okay? That's what the question is telling us. N is a member of natural numbers. So we do understand that natural numbers are basically counting numbers. So there was kind of an omission there. N is also supposed to be less than 4. We're interested in n being less than 4. Okay. So we need to list all the natural numbers from 1 to the ones that are basically less than 4. And the moment we just say less than 4, the natural numbers less than 4 are only 3. 1, 2, and 3. These are the only natural numbers less than 4. So now these are the values that are going to define the members of set E. So for the first one, we're going to plug in 1. So if you plug in 1 where there is n squared, you're going to have 1 squared minus 1 over 1 squared plus 1. 1 squared is 1, minus 1 is 0 over 2. So we have 0. Then for the other part, you put a 2. 2 squared is a 4, minus 1 is a 3. Then down there, 2 squared is 4 plus 1 is a 5. So we have 3 over 5. We can plug in the third one. 3 squared over 3 squared plus 1 minus 1. 3 squared is a 9. Subtract 1, it's a 8. 3 squared is 9 plus 1, 10. 8 over 10, which is 4 over 5. So we've listed the members of what? Of set E by looking at the set builder notation. So what we've listed there is, this is a form which you call the roster form. Okay. Yeah, so that is what we are basically saying. Let's try to move. The third question says, which of the following sets are empty? So before we get to identify which ones are empty sets, we need to first of all list the elements or take it to roster form, because that is basically easier for us to interpret than looking at the set builder form. So for the first one, what are we saying? X is such that x plus 3 is equal to 0. So we are told that our member of first set there is x plus 3. It should define that equation. Then the x should also be a member of natural numbers. So we know that natural numbers are counting numbers 1 going up, 1, 2, 3, 4, and so on and so forth. But then, what value of x can define that equation? It's x is equal to negative 3. So that is our possible member. But then, does it qualify to be a natural number? It doesn't. So if it doesn't qualify, so if there is no value of x that is able to satisfy the equation as well as meet the condition there, then the set is said to be empty. So for the first part, since the only value that can satisfy the equation is not a natural number, we can therefore say it is what? It is an empty set. Okay. Then moving on to B, x is such that 1 is less than x, then x is also less than 2, then x should be a member of natural numbers. So if it is just open, like there's no dash there, remember the moment we just put the dash down, it tells you that the numbers at the end are also included, but in this case they are not. So we're interested in the values of x between 1 and 2, and the values of x should be what? Natural numbers. So is there any natural number that is between 1 and 2? I'm assuming you said no. So there is no natural number in between 1 and 2. So even this set is empty. It's not possible to have a natural number between 1 and 2. So unless if we said 1 and 2 are included by putting 1 is less than or equal to x, x is less than or equal to 2, that would tell us to say that 1 and 2 are members, and we would basically just have 1 and 2 as the members in such a case. But in this case, it is an empty set because we are only interested in the ones between 1 and 2, and we don't have any natural numbers between 1 and 2. Okay. C. X is such that 3x plus 1 is equal to 0. 3x is equal to negative 1. X is equal to negative 1 over 3. Then the value of x should be what? Should be a member of real numbers. So for a set of real numbers includes all the numbers that we exist, all the rational numbers, all the irrational numbers, meaning that all the fractions, whether negative or positive, all the decimal numbers, whether positive or negative, they are all part of real numbers. So, is negative 1 over 3 a real number? Yes, it is. So, therefore, for set C, we do have a member, which is negative 1 over 3, and we therefore can say it is an empty set. It has got members there. Then finally, for the last one, so only one so far is refused. Only one is not an empty set. A, B was are empty sets. How about D? So for D, we are saying x squared plus 9 should be equal to 0. So x squared is equal to negative 9. X is equal to plus or minus the root of negative 9. So the moment we just say the root of negative 9, that ceases to be a real number. It's basically a complex number. Okay, it's basically a complex number, because if you try to simplify negative 9, the root of negative 9, this is the same as the root of 9 times negative 1. So at that point you can say you have root of 9 and root of negative 1. So you have 3, then you have root of what? Negative 1. So the root of negative 1 is the same as what? Is the same as I. So this is like 3i. So it's a complex number and not a real number. So we can therefore say that for the last one, it is an empty set, because they wanted the value of x that is able to define that equation, and it's a member of it's part of a set of real numbers. But in this case, the possible solutions to this equation are not real numbers, they are imaginary. So it's an empty set. Question 4. Which of the following sets is a singleton, or is singleton? So a singleton set is basically a set with a single member or single element. So for the first part A, they're saying x is such that x is an integer and it's from negative 1 up to x, up to 1, sorry. So we have from negative 1 to 1. So remember we said integers are positive or negative numbers. Of course, they don't include fractions and negative or non-decimals. So in this case, negative 1, 0, 1. So since we don't have an equal sign in between, we don't have dashes down there, that means that negative 1 and 1 themselves are not part of a set, only the integer in between. So there's only 0. So we only have one member for the first set. So therefore it's like what? It's a singleton. Then moving on to the second one, x is a member of integers, and x, so this was supposed to be x squared. So x squared minus 2x minus 3 is equal to 0. Then x should be a member of what? Should be a member of integers. So let's try to see the values of x that can define this equation. Okay. So what do we have? The product is negative 3, the sum is minus 2. The factors, negative 3 and 1. So we have x minus 3, and we have x plus 1 is equal to 0. So our value of x is, it can either be positive 3 or a minus 1. So we have two
two values of x that can define that equation, -1 and 3. So this one is not, it's not a singleton because it has got two members already. Okay, going back to C, we are told x to the power 3 minus 1 is equal to 0. Then x should be a member of what? Real numbers. So is it possible? So x to the power 3 is equal to 1. Then trying to find the value of our x there, it is only a 1. X is equal to 1. So how many numbers can you multiply 3 times by themselves to give us a 1? It's only 1 itself. If you get a -1, it is not possible. It's going to give us a negative value. So it's only 1. So we only have a single member for that one. So it's a singleton set. Then for the last one, x is such that x is a prime number. Then x is an even number. So we need to understand what prime numbers are and what an even number is before we get to C. So a prime number is a number that is divisible by 1 and what? And itself. It only has got two factors. So examples are 2, 3, 5, 7. 9 is not a prime number because it is divisible by 3, by 1, 3, what else? 9 is. So we already have 3 factors there, so it's not a prime number. So we can talk about 11, we can talk about 13. 15 is not a prime number because it is divisible by 5, 3, 15 and 1. So these are the common numbers. So and so on and so forth. We can talk about 17, 19. All those are prime numbers. So even numbers on the other part, these are numbers that are divisible by 2. They don't give any remainder when divided by 2. So we have 2 itself. We have 4, 6 going up. So if you try to compare these two sets, there is only one number that is both a prime number and an even number, which is just set 2. So the last set is also what? A singleton. Question 5. Which of the following sets are finite and or infinite? So we're trying to determine whether it has got a set has got a limited number or unlimited members of elements. So talking about a set of Algebraic universities in Zambia, are they known or they are not known? So by finite, meaning that we know the exact number, or the number is countable. Infinite, we can't count, we can't get to the end. Finite, they are basically known. It's a number that is determinable. For infinite, indeterminable. So sets of Algebraic universities in Zambia, so they are known. The university is in a country or a nation. It's a number that is determinable. So it's a finite set. We're able to count. Then the sets of animals living in Zambia. So is it possible to know is it determinable or indeterminable? So it's basically determinable. We're able to count. Okay. Then 1, 2, 3 without ending. So we don't know the ending point there, so it's infinite. We don't basically understand the end. And numbers don't end. Then the set of lines which are parallel to the y-axis. So what is the y-axis? So if you go to the xy plane or the Cartesian plane there, so you're trying to look at the numbers that are the lines which are parallel to the y-axis. So this is the y-axis. So the set of lines. So there can be a lot of lines that can be parallel to what? That can be parallel to the y-axis. So these lines are infinite. We can't determine them. Okay. So basically finite just basically talks about things that you're able to count, determine, infinite things that you don't know the ends. Okay. Okay, question 6 requires us to write down the power sets of each of the following. So what is a power set? So you need to understand that basically a power set is a set that consists of what? It lists or what? All the subsets of a given set. So it's a set that is consists of what? Consists of all the members or all the subsets. So I can start with A there. If I look at A, we do understand that the subsets are given by the number of elements. Okay, so it's 2 to the power n, where n is the number of elements in a given set. So it's 2 to the power 2. So we have 4 subsets for A. So what are these subsets? So therefore our power set for A is going to be, so what do we have? So the first one is 10. We can put 11. So if you don't understand how to come up with subsets, basically a subset just any set that you can come up within a given set. So you can list each member separately in a given set. Then you can also combine them, write it the way it is, and also include an empty set. So I've already separated them. Then I can also write the actual set itself. Then I can also add an empty set. So how many subsets are these? These are 4. So that is our power set for A. Our power set for B, so we have got 3 different members there. So the number of subsets basically that we expect there is 2 to the power 3, which is going to be 8. Okay, so the first one that I'm going to use will just include single elements, P, Q, R. Then I can also combine. I can come up with a set of 2, 2. So P can be with Q. P can also be with what? With R. So if P can be with Q and P with R, even Q and R can be together. Okay. So all of these are already combined together. Then we can write the set itself, which is just PQR. Then what else? An empty set. Are these already 8? So we have 1, 2, 3, 4, 5, 6, 7, 8. So we've listed all the members there. We are already 8. So that's how you come up with the power set. So feel free to pause the video and try out the third one. So for the third one, how many members are there? So we have 2, 3, and 3 and 7. So since 3 and 7 is those are in brackets, we'll consider them to be a single member. So we have 3 members there. So a number of subsets as well that we expect is should be what? Should just be 8. So we can list them. Power set of C. 2 can be alone. 3 can be alone. Then 3 and 7 can also be alone. What else? We can now combine these guys. Can combine them. I can combine 2 and 3. I can combine 2 and 3 and 7. So remember 3 and 7, I'm writing it to be a single element there. Okay. Then we've combined 2, 3 and 7 with 2 and 3. So I can also combine 3 and 3 and 7. So I'll combine that as well. 3 and 7. Okay. So what else? We can write the set itself. Then an empty set. Are these already 8? 1, 2, 3, 4, 5, 6, 7, 8. So that is how you come up with the list of or come up with a power set. A power set consists of just a subset of given set listed together in a single set. Okay, let's go over performing some basic operations on sets. So this is a very simple question. In this case, we've been given the members of we've been given the universal set. Okay, so we've always said when you're talking about a universal set consists of all the elements or all the members that are under discussion. So we are from 0 to 10. Then we've been given our A to consist of those members, our B, our C, and our C. So then the first part of the question is asking us to list B complements. So I've seen some students who basically gets to come up with a Venn diagram when they are given such a question. So that's basically very much okay. It helps to simplify your work. But I also don't see anything wrong by just going directly. So when you think of B complement, list your B. For your B, you've been given 2, 4, 6, 8, and 10. 2, 4, 6, 8, and 10. These are the members of B. But we're interested in the B complement, so I'll put a complement outside. So a complement means that the members that are not in this set, but are within the universal set. So if you look at the universal set in this case, we have from 0 all the way up to 10. So let's try to exclude 2. So we can remove 2. I'll put dots there. Remove 2, remove 4, remove 6, remove 8, remove 10. What members are going to remain? So we're going to remain with 0, 1, 3, 5, 7, 9. So that is our B complement there. And what you need to understand is that when you get to combine, this is why we say if you combine B unionize with its complement, it's supposed to give you the universal set. That's the main idea there. So if you count the number of elements in the universal set, we are from 1 to 10 plus 0, so 11 members. So equally, when you get to add the members in the B complement and B, you need to have what? 11. So we have 1, 2, 3, 4, 5, 6. In B we have 1, 2, 3, 4, 5. So 5 plus 6 is 11. And that proves that combining any set with its complement is basically equivalent to the universal set. So we've answered the first part. The second part is asking us to find A intersection B. So A intersection B, basically we get to look at the common elements between A and B. And my advice is for you to list your A. In our A we have 2, 3, 4, and 5. Then for our B we have 2, 4, 6, 8, and 10. So for the intersection, we are interested in the common elements. So look at the two sets. What are the common members of these sets? So I can see that 2 is common. I can also see that 4 is common. Is there any other element that is common between the two sets? So our answer, just have 2 and 4 for A intersection B. In a case of where they maybe, of course it has not been given in this case, where they ask you to find A intersection B, then the complement of it. They're interested in the elements outside the intersection. So knowing that in the intersection you only have 2 members, and in the universal set you have 11, so you just need to remove the 2, and you expect to have 9 members, which will be 0, 1, 3, 5, all the way up to 10. You only exclude the given set if you're talking about the complements of that set. Okay, we are on the third part of the question, which says B union C. So for B union C, we get to combine the elements in B with C. So for our B, we have 2, 4, 6, 8, and 10. Then our C, we have 2, 4, 5, and 6. So the union of the set basically involves you combining the elements together. You combine the elements together. So the set that you're going to have is the union of the two sets. So you only list the common elements once. You don't have to write them twice. So for example, if you look at 2 and 4, 2 and 4 are common, so just write them once. Then I'll go to 5, 6. Then I'll get, so 6 is common. I've just written it once as well. Then I'll go to 8 and 10. So we've combined all the elements in B with C. That is what the union of the set asks you to do. Okay. Now let's try to move to the fourth one. We see what we're going to do there. So A complement union C complement. So basically, according to our De Morgan's laws, we are told that the union of two complements of a set is the same as what? The intersection of the two sets. Now its complement. So I think that is actually even better and easier. You get to save on time when you have A intersection C. So for the A intersection C, you need to look at the elements that are common in A and C. So I can see that 2, 2, 2, 4, A and C. 2, 4, even 5 is also common. So 2, 4, and 5 are the common elements in A and C. So now the complement of it would mean that you exclude the 3 elements from the universal set. So in the universal set, if you look at the entire universal set, remove 2, 4, and 5. What remains is your solution. So you have 0, 1, 3, 6, 7, 8, 9, 10. So these are the members of a given set there. If you want as well, you can decide to just like list your A complement. So if you look at your A complement, you are trying to remove 2, 3, 4, and 5 from the universal set, and what you are going to remain with is 0, 1, 6, 7, 8, 9, and 10. Then you are also interested in C complement. For your C complement, you will need to exclude the members in C, which are 2, 4, 5, 6. So you are going to remain with 0, 1, 3, 7, 8, 9, 10. So if you get to combine these elements, combine them together, you're going to have 0, 1, you go to 3, you go to 6, 7, 8, 9, and 10, which is basically matching up with this because you're trying to find the union of these two sets. So you just get to combine the elements. So I don't know which one seems easier, but I look at the case where you have them in brackets to be easier because you get to save on time. Then for B minus C, B minus C means B without C. Others could interpret it to be B intersection C complement, so whichever works for you. But I look at B minus C itself to be easier because for our B we have 2, 4, 6, 8, and 10. We are trying to subtract our C. For our C we have 2, 4, 5, and 6. So the basic idea is when you are trying to find B minus C, you just need to exclude the members that are in C from B. So in this case, I can see that 2 and 4 can be excluded because they are part of C. So they are supposed to move from B. 6 is not, 8 is not, 10 is not. So that remains. That is what is going to remain in our B if we remove the members in what? That are in C. That is what it means when you say B minus C. The other way of thinking about it is think of the elements that are in B and are not in C. Okay? Then the other way is by comparing what is outside C and what is in B. You get to find the intersection between B and whatever is outside C, which is also okay. Then looking at the last one, what is the last one asking us to do? For the last one, it looks complicated, but it's not. So you have x minus c complement intersection a minus b. So for your own information, in this case, x is denoting the universal set. So we are assuming our universal set is x. So how do you get to simplify that? So what we're basically going to do is we'll say our x minus c is basically, it's like what you have is you have your universal set. This is your universal set, then you have your c there. So if you subtract or remove set c, what is going to remain is everything outside c. So it's basically c complement. So if you remove any given set from the universal set, what remains is the complement of that set, because it's either you are part of the set or you are outside it. Or the other way that you can think about it, you can also say, remember, so x minus c is the same as c complement, so I'll put, there's also a complement outside that I have to show. Then the other way you can think about it is x minus c is the same as x intersection c complement. So any set intersected with a universal set is that set, because every set is part of itself as well as part of the universal set. So this is equivalent to what? To c complement. So still it stands c complement, and there's also a complement outside. So this turns out to be just what? Our c being intersected with a minus b. So at that point it becomes easier to simplify, because all you have is just c being intersected with what? With a minus b. So what is our a minus b? A minus b requires you to exclude all the members that are part of b from a. So in b we have 2, 4, 6, 8 and 10. We need to remove all these members from our a. So we've seen that 2 and 4 are also in what? In a. We'll remove them. 5 and 3 are not, so we are just remaining with 3 and 5 for a without b. Then for our c, we have 2, 4, 5 and what? And 6. So the intersection of the two sets gives us what? Gives us a 5. And that is our solution to that question. Finally, in this video, our last question is basically focusing on the set interval notation, where we get to look at a set of real numbers. Okay, so if you've not understood, or this is the first time that you're coming across set interval notation, I would advise that you check out our tutorial on set interval notation, the introduction. Okay, so let's get to solve the question. So in this case, the key things to note are that we've been told to say our universal set is basically from -3 to +9. So whenever we are using these brackets, it basically tells us to say that -3 and 9 are what? Elements or members of that set, or members of a universal set. So now, to start with, the first question is saying find a complement. How do you get to find the complement of a set? So remember, for our universal set, it is moving from -3 all the way up to 9. Then for our a, we need to, for us to find a complement, we need to display our a. So our a is moving from -1 to 5, somewhere there. So we need to understand where we need to shade and where we will not shade. So where are we supposed to shade? -1 to 5. So 5 is what? Is supposed to be shaded. Then -1 is not going to be shaded because of the brackets that are there. So in such a case, it means that -1 is not part of a, then 5 is part of a because of. So when it's empty, it tells you that it's not a part of the set. So we have our a there. So the complement of a set includes whatever is not part of that set, but within the universal set. So it's going to move from this point to that point, and from this point to that point, because that is the region that is not part of what? A. So that is our A complement. We have two sides. So now, we've said when it is not shaded, -1 is not part of A. So if it is not part of A, it is therefore going to be part of what? It's going to be part of a complement. Then 5 is part of A, so it can be part of a complement there. So we'll not share that part. So it's like you get to do the opposite. So how about the ending points? For the ending points, you basically get to do what is given in the universal set. So -3 is part of a universal set by looking at those brackets. So since it's part of a universal set and not part of A, it is also part of a complement, because the complement consists of all the elements in the universal but not within the given set. So equally 9 is also part of a complement. So if our universal set was like that, in that form, would have not what? We would have not shaded the ending points, because that would tell us to say that -3 and 9 are not part of the universal set. Okay, so let's try to focus on what we've been given. So we've displayed it on the number line already. Now how do we get to list it? So our A complement in this case is equal to, so we're moving from -3 all the way up to -1. So now the question is, are they part of the complement? Look at it. If it's shaded, then they are. So what is shaded, that is also shaded. So we use these brackets. So union, we combine it with the other part from 5 to 9. So at 5 is not part of a complement, 9 is part of a complement. So if you shade, understand what brackets to use. If it is not shaded, understand what brackets not to use. Okay, so we've dealt away with our A complement. Then to make things easier, for the second part we've been given B complement, union C complement. So according to De Morgan's laws, what is that supposed to be equivalent to? So we understand that it is going to be B intersection what? C complement. Okay, so I would go for that because that is going to be easier and it will save on our time. So B intersection C, B is moving from what? So for our B, we've been told it's moving from 3 to 7. From 3 to 7. So 3 to 7, that is our B. Then 3 is a member because it is, we're using a square bracket there, so we'll shade for 3. 7 will not shade, so what is guiding is the bracket that I used there. So that is our B. Then for our C, we are moving from as low as -2 all the way up to somewhere 8. 8 is somewhere there. So from -2 all the way up to what? To 8. So none will not shade any side because both -2 and 8 are not part of a set. So therefore, for the intersection you need to go for the common region, which is part of both sets. So it's this region. That region is overlapping, so it's between 3 and 7. And what will guide you is the smaller what? The smaller set. So the smaller one is moving from 3 to 7, and I'll use a square for the left hand side. And for the right one, I'll use a curved. So why am I using a curved? I'm using curved for 7 because 7 is not a common member. It is not part of what? B, because it is not shaded there, but it is part of what? But it is part of B. So 7 is not part of the intersection of B and C. So if we are saying that is our intersections, we are not interested in our intersection in this case. We are interested in its complement. So you can display that again. So for our B intersection C, it is moving from 3 to 7, where 3 is what? Is part of the intersection. So this is our B intersection C. So for its complement, it's going to consist of every region that is part of a universal set. So our universal is moving from -3 up to 9. So therefore it's going to move from this part to that end and from this end to that end. So the ending points matches up with the universal. Since -3 and 9 are part of a universal set, they are also going to be part of a complement because they are not part of the intersection. So say this is our B intersection C complement. That is also our B intersection C what? Complement. Then this part is also supposed to be shaded because 7 is not part of the intersection. So it's therefore going to be part of what? The complement. So listing it down, what would we say? So the first part is we're moving from -3 to 3, where 3 is part, then 3 is not, union. The other part we are starting from 7 all the way up to 9, where both 7 and 9 are part of a complement. That is the way you get to approach such a question. Moving on to the third one, the second from the last, it's A intersection B minus C. So it's very advisable that you get to start with whatever you're given in the brackets. Okay? So what have we been given in the brackets? In the brackets we've been given B minus C. So what I'm going to do first of all, I'll show my B. My B is moving from 3 to 7. Okay? From 3 to 7. So from 3 to 7, that's for our B, where 3 is part and 7 is not. So what is our B? So now, what we're trying to do is we're trying to exclude now C. Every region that is part of C is going to be removed. So C is moving from as low as -2 all the way upwards, all the way up to 8. All the way up to 8. Imagine. Now, again, it's like, what are we trying to do? You're trying to remove B. You're trying to remove B. Or you're trying to remove C from B. So it's like the entire region of B is part of C. So if you remove C from B, if you remove every entire region that is part of C from B, it's like what you're going to remain with is an empty set, because it's like nothing else will be part of B if we exclude C from B. It's like B is kind of a subset. It's like it's just part of C if you get to look at what we have or what we've sketched there. The other way that you can think of is B minus C is the same as what? B intersection C complement. So if we come up with a C complement, guys, it's like going to move from this point all the way up to the ending point, which is in this case is a -3. That is for a C complement. Then the other party to move from that point all the way up to what? All the way up to 9. That is our C complement. So now we need to find the intersection between the C complement, which are these ones, with the B. Is there any intersection between the two sets? So there is no intersection. There is no overlapping. So in other terms, what we're trying to say is basically B minus C in this case is an empty set. Okay? So A intersection complement set, you can't combine an empty set with any set. There is no intersection between an empty set and a given set. So it's just an empty set as well. So that is our solution for our third part of the question. Moving on to the last one. For the last one, it is x minus c complement. So this is kind of just related to the previous question that we looked at. Remember, if you look at the last question, this is what we had. And simplifying it, this is what we had. So we're just going to have x minus c. We said any set being removed from the universal set basically is the complement of that set. That's what gets to remain. Okay? Then complement just becomes c. So that is what we have now. So we have C intersection A minus B. We have our C there. Do we have A minus B? No, we don't have our A minus B. So A minus B means A without B. So our A is moving from -1 to 5. That is our A. Then 5 is part of A. We shade. That is our A. Then our B is as well is moving from 3 to somewhere 7, where 3 is part of B. So that is our B. And this, so for our A minus B, we need to exclude every region that is part of B. So all this region is part of B so we'll cut it out, and whatever is going to remain is going to be our A minus B. So now, since 3 is part of B, it can be part of A. It can be part of A. So for our A minus B, it's going to be the part of A without what? Without B. So if we can remove the B away. So since 3 is part of B, it is not going to be part of A. So we'll not shade the 3 parts. So that's going to be empty, meaning that it has been taken by what? The B, because we said A without B, or A minus B. Since 3 is part of B, it can be part of A. So that is our A minus B. Then we need to intersect this with our C. Our C is moving from -2 up to 8. So I'll write it. So that is our what? Our C. So the intersection is the region that is overlapping. So this is the intersection. So that is our what? C intersection A minus what? B. So describing that using set interval notation is basically just stands out to be, or even in terms of shading, the common region is the one that is going to remain there. This is your intersection. So listing that is just basically from -1 to 3. So that is our intersection. So this marks the end of our tutorial. I just hope that you've it was a quick catch up and a recap on what you already know under set theory. Thank you very much for watching.